queries for the things which we discussed in the last class? Sarthak and Arpit?
No.
Okay. So let's wait for 1 or 2 more minutes and then we start. So let's quickly recall what we did in the last lecture. So we were discussing the RK methods, the Runge-Gupta methods for finding the approximate solution of the initial value problem. Which we also denoted by RK method. So this is a shorthand notation which we are using for the Runge-Gupta methods. So the first method, or so the class of the method which we saw in this direction is the RK method of order 2. And what was the form of this RK method? And in particular for the order 2. So we are going to compute the approximation of y at xk plus 1, which is nothing but the yk plus 1, and it is given by yk plus h times the average slope, right? So the average slope we denoted by capital F, which is basically depending on xk, yk, and it will also depend on f and h, but I skipped writing f because it is understood that I meant here the average slope, the slope here. Okay, and in particular for this RK method of order 2, we have that this function f is given by, so this is, we are taking it as a, so we are having the factors gamma 1 and gamma 2, and then we are taking gamma 1 times f and gamma 2 times x. So we are introducing the parameters here as well. This is y plus right, and then we obtained that, so by imposing the condition that I want my truncation error to be of order 3, right? So by imposing this, we could determine these parameters gamma 1, gamma 2, alpha and beta, right? And we obtain that the gamma 1 is 1 minus gamma 2, alpha is 1 divided by 2 gamma 2, and beta is also the same as alpha. And alpha 2 is gamma 2 is arbitrary here, right? So for any gamma 2 which is non-zero quantity, we have that this method with these parameters, this is going to be of order 2, right? And in particular, if we took gamma 2 equals 1 by 2, we obtain that yk plus 1 as yk plus half k1 plus k2, where k1 is h times f of evaluation of f at xk yk, and k2 is h times f evaluation at xk plus 1 yk plus k1. Okay, so this was the idea of the RK method of order 2. Basically, this is the one parameter family, and then parameter here is gamma 2. All right, so The most commonly used method in this family of the RK methods is the RK method of order 4. What is this method? Let's first write down its formula. So I'm not going to derive the formula, I'm just going to explain it, okay? So underlying idea remains the same, that you will be starting with the yk plus 1 in this form. Then we will have some choices, like f will change here. When we are going to the RK method of order 4, f will change, and it will involve some parameters which will be denoted, which will be determining, so that the truncation error is of order 5, okay? Because this method is of order 4. All right. So the formula for this method is given by so again we want the approximation of the exact solution y at xk plus 1, which is yk plus 1, and it is given by yk plus 1 by 6 k1 plus 2k2 plus 2k3 plus k4. Now these ki's here are defined as, so k1 is h times f evaluation at xk yk, k2 is h times f evaluation at xk plus h by 2, yk plus k1 by 2. Note that we have already computed k1, so k1 is known here, so you can compute k2. Now using k2, I'm going to compute k3, so which is h times f evaluation at xk plus h by 2, yk plus k2 by 2, and k4 is h times f evaluation at xk plus h, yk plus k3. Okay, so once you have found k1, so note that knowing xk, yk, you will evaluate k1, and once you have k1, you can evaluate k2, and then using k1, we can get k3, and using k3, we can get k4, and once you have k1, k2, k3, k4, you substitute in this formula, and then you will get yk plus 1. Okay, so for this method, the truncation error, the local error basically, is of order h raised to power 5, and the global error is of order h raised to power 4. And this, what we are writing here, this is how you will determine the parameters which we will be getting in the form of the y f. Okay, so now you might be wondering that what f is going to be, right, in this case. So what I have to choose that I can get this formula. So let me state a general form of the f, that is, let me state that suppose you want to get a method of h raised to power p. Okay, then what f you have to take? So in particular, it will you can take the table value of the p so that you get RK method of order 4 as well. So let me just write it as a remark. So in general case, the choice of the function f is given by, so again you can guess that it is going to be some average slope. Okay, so let's write it down what that the slope we are going to consider. So So this is going to be, so let me write it in the form of summation, because this I'm writing it for the method of order P. Okay, RK method of order P. So it will be, so we'll have a constants, let's call them gamma j's, because we used gamma 1, gamma 2 in the case of the RK method of order 2. So let's take gamma j's, gamma j times Vj, and j will be varying from 1 to p, and Vj's here are going to be, so V1 is f of x5, and for other j's, Vj is going to be f x plus, so I have to take some coefficients, so I used alpha there, so let me use alpha j's times h, and then y plus h times, so we used beta there, so I'll use the index based on beta, so beta, so I'm going to have two summation j, and then I'm having a summation over I, so I'm going to denote the indices as ji, vi, and I is ranging from 1 to j minus 1. Okay, and these, what are the unknowns here? So you have gamma j's as the unknowns, alpha j's as the unknowns, and beta ji's as the unknowns, right? So where we determine the unknown constants so that the truncation error is of order p plus 1 in this case, right? So you will have okay. So, but you can guess that like even if you want to do this for the order 4, the things are going to be a little cumbersome because you will have lot many parameters and you have to determine them. So, but this is how it works. So underlying idea remains the same, what we have discussed here for the order 2. If you are clear with this, you will be able to do it even for the order 4. Okay. Now, just to mention that you can see that we can get the method of any order using this approach. That is, we have a RK method of any order you say, order, whatever order you mention, you can derive a method of that order, right? So this is a very like advantageous thing with the RK methods. But if you observe, even for the order 4, right? So how many functional evaluations you are requiring? So for one step, you have to do here itself. You can see in K1, K2, K3, K4, you require the functional evaluation at with the different arguments, right? So it's not that I have computed f of xk and that's what I'm using in the next step. You have to compute this again, right? So this is the only drawback with the RK methods, that you require a lot many functional evaluation as you increase the order of the method. Okay, so this is a major disadvantage with the RK methods. So let me just point it out here. So the disadvantage which we have, so that's a major disadvantage of the RK methods is that they use many more functional evaluations. So many more evaluations. So evaluations of the f, and f is nothing but the, so evaluations of, which is nothing but the derivative of y, right? So evaluations of f to attain the desired accuracy. Okay. So let's take one example and just try to solve it to understand that how does this method really works. So we are going to consider this initial value problem. So the differential equation is given by y prime equals y, and the initial condition is y at 0 equals 1. Okay, so you have to use RK method of order 4 to find the approximate value of y at the point. So we are starting with the 0 and I want it at the point 0.04 with h equal to 0.01. Okay, so we have 0.01, 0.02, 0.03, and then 0.04. Okay. Okay, so let me do it for order 2 itself, and 4 you take it as an exercise because it will require not many calculations. Okay, so let's solve it. So when I refer RK method of order 2 without mentioning what is the choice of the gamma 2, it means that I am referring to the case gamma 2 is equal to 1 by 2. Okay. So this means that I have that yk plus 1 is given by yk plus 1 by 2 of k1 plus k2, where k1 is h times f evaluation at xk yk, and k2 is h times f evaluation at xk plus, so what it is, half. Xk plus 1, yk plus k1, okay. Xk plus 1, yk plus k1. Okay, so now let's formalize the things here. So we have been given this information. So this is x0, this is x1, x2, x3, and x4. And what we have to find is the approximate value of y at the x4. So which is going to be, so basically we have to find y4. Okay, so we have h equals 0.01 and x0 is 0. Y0 is y at x0, which is given to be 1. So let's find out what is y1. So y1 is going to be y0 plus 1 by 2, k1 plus k2, with k1 as h times h. F is, so this is your f. So fxy is simply y here. Okay, so we'll get k1 is h times f evaluation at xk yk, so which is x0 y0. So this will be simply h times y0, which is y0 is 1. So this is simply 0.01. And k2 is h times f x1 y0 plus k1. So this is going to be h times y0 plus k1. And y0 is 1. K1 is 1.01. So you multiply by 0.01. So you will get 0.01010. Right? So therefore, you just have to substitute here. So y0 is 1 by 2 of these two quantities, k1 plus k2. So upon simplification, we get it. So let me check what I get. So this is 1.01005. Okay, so you have found y1. Now you repeat the same procedure. You can find y2 as y1 plus 1 by 2, k1 plus k2. Now k1, k2, they're not the same as k1, k2 what we have here. They will depend on the nodes x1, y1 now. So we will have k1 as h times x1, y1, which is simply h times y1. And y1 is known to us. So this is going to be 0.01. 0.01005. Okay, because h is 0.01. So we have this, and now you can find k2 as well. So k2 is h times f of x2 y1 plus k1. So which is h times y1 plus k1. So which is going to be, so you can verify this is going to be 0.0102015. Okay, so you substitute here these two values in y2. So y2 you will get it as 1.020201. All right, now you repeat this procedure, and this you can do it yourself. So you can find the values of the y3. So value of the y3 is going to be, you can verify that this is going to be 1.030454. And then finally you use y3 to compute y4, which is going to be 1.040810. Okay, so this is the approximation of y at x4. All right, this is what we wanted to find. Now, one more step you can do is that you can find an exact solution of this problem, right? So this is a simple problem. You can find its exact solution, and you can substitute. Suppose you found the exact solution that is going to be in terms of x, and you can take x is equal to 0.04. That will give you the exact value of y at 0.04, and you can verify that whether you get a close approximation of using this y4 or not. Okay, and the second exercise is that do this problem using Archi method of order 4. All right, so see, once you will have the exact solution, you have found the value of the approximate solution using Archi method of order 2. Now you will also find the approximate solution using the Archi method of order 4. You can see which one is much closer to the exact value. So of course, you're using the method of higher order here. So you expect that this will give you the better approximation of the exact solution than the method of order 2. Okay, so that you can verify once you have got the exact solution. All right, so so what we have done, let's quickly give a review on that. So knowing the, if you see whatever methods we have discussed so far, we have computed, say, the information at the level xk, that is we had the yk, and then we used that to compute the information at the level to xk plus 1, that is we computed yk plus 1 using the information at the one previous level, right? So basically to compute yk plus 1, I'm just requiring the information for one previous step, right? So that's the reason these methods are called single steps method. Okay. Now there's another class of the method which is called multi-step. So let's first understand that how these method differs from the methods which we have discussed just now. So let's write down the same thing what I have written here, and then I'll differentiate that what do we do in the multi-step. So the methods which uses information only from the previous step, means the last computed point, xk, yk, to compute the next point, which is xk plus 1, yk plus 1. These are called single step methods. Right? And then it was further realized that you can get a better approximation if you, why to just use the one previous step, right? You have the information up for the label yk plus minus, yk minus 1, yk minus 2, like that, right? So why don't you make use of that information as well? Okay, so it was realized that you can get better accuracy by using the information which is available at the earlier steps as well. Okay, so the methods which are going to use more than one step, that is, you're not just using the information at xk, yk, you are going to use the information at yk minus 1, xk minus 1, yk minus 1, and the previous step, like that, right? So these methods are going to, we are going to call them as multi-step, right? With the obvious reason that we are using the information from multiple steps. Okay, so the methods which uses information from more than one previous points to compute the next point. These are called multi-step methods. Okay, so I'm just going to discuss two methods from the family of the multi-step methods. So underlying problem remains the same, that we want to solve this initial value problem, that y prime equals f of xy with y at x naught equals y naught. Okay. So let's understand that what do we do in the multi-step method, right? So it's like, it's a class of the method, but the underlying idea is the same. If you are clear that what do we do, it's just that it's just the calculation part then. Okay. So again, as we have derived, say, the modified Euler's method, and we have realized other methods as well, that this also uses that integral equation. Okay. So we are simply going to integrate. So if we call this as 1 and this as 2, so if we integrate 1 over the interval xk to xk plus 1, so what do we get? So we will get y at xk plus 1. This equals y at xk plus integration from xk to xk plus 1 of f x yx dx. Okay, so it just simply I integrated the equation 1 from xk to xk plus 1. All right, so let's call it 3. So if we denote, so note that this y is also a function of x and f is all, so here f is depending on x and y both. So so this completely, this is going to be a function of x itself. So let me call this as gx. Okay, so if I want to derive a method, it's just that I have to find a suitable approximation of this quantity, right? So basically, now we have to evaluate the integration xk to xk plus 1, f we are denoting it by g dx, right? So what do we do in these multi-steps method? We approximate gx by the interpolating polynomials, right? Like you have seen in the case of the modified Euler's method as well, that we use the trapezoidal rule there, right? So here these methods are also going to use the interpolating polynomial to find the approximate values of this integral. Okay, and how do we do it? And what differs here is that the points which you are going to use for the interpolation. Okay, so let's just see that. So we have to evaluate this integral. What do? We approximate gx by interpolating polynomial. And then integrate it. Okay, so this is the underlying idea. Now, based on that, how you're going to choose the interpolation points, based on that, this multi-steps method, we can have a categorization of them. So I'm going to explain 2 methods in this class. So the first method is the Adams-Besford method. Okay, these are also referred as AB methods. Okay, with the like A being taken from the Adams and B being taken from the Besford. So what do we do in this method? So we basically use suppose we have to derive a method of order. So let me write it down and then I explain it. So for a given non-negative integer, it's denoted by Q, AB method. So so again, this is not just one method. This is a class of the methods. Okay. So these methods use an interpolating polynomial of degree Q with the nodes So what is the set of nodes we are going to take? So I will, as I said, I'll not just stop at xk, I'll go further. So this is of degree q. So I need, how many points I need? So if I want a polynomial of degree q, I need the information at how many nodes?
Q plus 1.
Q plus 1, right? So I'm starting with xk and I'll go in the backward direction. So I'll take xk minus 1, xk minus 2, up to xk minus q, right? So these are q plus 1 points. So you can determine a interpolating polynomial of degree q, and that you use to approximate the gx and finally to compute the integration of that. Okay, so we use these points. So AB methods use an interpolating polynomial of degree cube with the nodes this to approximate gx in. So let's give it a equation number. So this is 3, this is 4. Okay, so let's call it, sorry, we already have 3. So gx in 3. All right. So again, I'm going to explain this method, like what exactly we get the method as for the simple case. That is, I'm going to take q is equal to 1. And whatever we understand for the case q equal to 1, you can do it for the general case. Okay. So q equal to 1, meaning I'm taking a linear interpolating polynomial. So the linear interpolating polynomial so what are going to be the nodes? So when we take q is equal to 1, we just have xk and xk minus 1. So this is given 1. We can write down the expression of it. So I'm denoting it by p1x. So this is going to be, so let's write down, since we are at the simplest case q is equal to 1, so we can simply use the Lagrange interpolating polynomial. So it is going to be xk minus x divided by, because I have length as xk plus 1 minus xk, right? That is, we are still considering the equally spaced points. So this is going to be xk minus 1. Okay, so this will be the same as into g evaluation at xk minus 1 plus x minus xk minus 1 divided by xk minus, yeah, this is correct, xk minus 1 into g at xk. So this is also h and this is also h. Note that I have taken the minus sign out, right? So we would have xk minus 1 minus xk, and in the numerator we would have had x minus xk. So I've just cancelled the minus sign so that I can have h here. So basically we have, this is 1 by h times xk minus x, g at xk minus 1 plus x minus xk minus 1, g at xk. So this is what p1x is. So we want to find, so this is the approximation of g, right? And we have to find the approximation of gx over the interval, the integration over the interval xk to xk plus 1. So its approximation is going to be xk to xk plus 1 p1x dx. Okay. So we can simplify this, that what is the integral of p1x over the interval xk to xk plus 1. So this is going to be 1 by h integral xk to so g is a g at xk minus 1. So this is a constant, so I can keep out of the integral. So integral will be from xk to xk plus 1 xk minus x dx plus g at xk integral xk to xk plus 1 xk minus x minus xk minus 1 dx. Okay, and you can simplify this. You can just, this is a linear polynomial, so you can integrate it and substitute the limit. And I'm just writing what you get upon simplification. So we get this as 1 by h. So this is going to come out to be, so you will get this as minus h square by 2 g at xk minus 1. And then this factor will come out to be 3h square by 2 times g at xk. Okay, so we get, upon simplification, this is 3h by 2 g at xk minus h by 2 g at xk minus 1. So this is the integral of xk to xk plus 1 p1x dx. Okay, and we also know the interpolation error, right? So this will give, so whatever the error is involved here, that is what I'm writing approximation, I can write down if I add the error terms as well. So I will get equality there, right? So let's see what is the error. So the error is going to be integration xk to xk plus 1 gx minus p1x dx, right? Let's call this as E1 of the g. Now, this is like, following with the same steps as we have done in the case of the trapezoidal rule, right? When we obtained the trapezoidal rule, only thing is that, of course, what have changed is that P1 acts like we are on this interval xk to xk plus 1. So it's not using the xk and xk plus 1 as the nodes, rather it is using xk minus 1. So that's why you see the difference here. Now, but the underlying ideas are the same what we have used there. So how do we simplify the error? What should we do? So we have in terms of the Newton's divided differences, right? We can write down the interpolation error. So what it is? Tell me. So if you use, for this, we are having this as an interpolating polynomial. So what is the error? Interpolation error in terms of the Newton's divided difference.
X minus xk into x minus xk minus 1.
Okay. And then you will have f
Derivative.
with the arguments xk minus 1, xk and x. Sorry, g. Okay. So now to simplify, what do we do? The integral mean value theorem. So can we apply it here? So we are integrating over the interval xk to xk plus 1, right? So x is always greater than or equal to xk. So which means that this quantity is going to be always
greater than equals to 0.
So you can apply the integral mean value theorem. So basically I can take out the factor with this, with at x equal to some xi, right? And then I will use the relation between the divided differences and the derivatives, right? So what you will get this as, so this will be some g double prime at some xi k divided by factorial 2. So an integration xk to xk plus 1, x minus xk, x minus xk minus 1 dx. And you can integrate this quantity. Okay, so upon simplification, you will get this as 5 by 12 h cube dg double prime xi k, where xi k lies between xk plus 1 and xk plus 1. Okay, Therefore, what you can see from here, that if I want to see that integration of G is basically the integration of the P1 plus this factor, right? Integration of xk to xk plus 1, P1 plus 5 by 2 h cube G double prime h jk, right? This you can observe directly from here. So I'm taking the P1 factor to the right hand side. All right, so we have this. So therefore, if I substitute it back to this equation, which is equation number 3, so therefore, from equation 3, we get, so keeping in mind that gx is nothing but f of x, yx. Okay, and for this integral, we have already got this expression. So let's substitute it there. So we have y at xk plus 1. This is the same as, so we have y at xk plus this integral of g over xk to xk plus 1. So this is y at xk plus this integral. This is the same as, so let's write down this value of this integral of the p, this one. So h by 2, 3 times of f. So g at xk, right? So which is nothing but the f of xk, y at xk, minus h I've taken out, so it will be f at xk minus 1, y at xk minus 1, plus 5 by 12 h cube. So g, if you try to see, g is f, right? And f is y prime. Okay, so double derivative of the g, this means that we are going to get the third derivative of the y at some jk. Okay, so this is what we have got. So from here, we can derive what the numerical method has to be. So therefore, AB method is, so I'm going to compute yk plus 1 as yk plus h by 2, 3 times f of xk yk minus f of xk minus 1 yk minus 1. Right? So basically, I've used this expression to define this method. Okay. So let's give it equation number. So let's call this as 5 and this as 6. And what k has to be here? Can you specify that k has to be greater than equal to what? So note that you have a yk minus 1 as well here, right? So k has to be greater than equal to 1 because you know the information from y0. Okay, and if you just try to see the what is the lowest value of the yk, you can compute from here. That is what is going to be the lowest value of k, whether that is 1. Basically, you will be able to compute y2. That is the first approximation you're going to get is y2 using this formula, right? And y2 is going to require both y1 and y0, right? So that is, we need the y0 and y1 to compute y2. Okay, but what is known to you is only y0, right? Now you'll wonder that, okay, what should we do to find the value of the y1? Because you cannot find the value of the y1 using this formula, right? So to find the value of the y1, you can apply the single step methods. Okay, so you know the y0, so you apply the single steps method to find the approximation y1, and then you have the both y0 and y1, and then you can use this formula to compute y2 and onwards. Okay, so both y0 and y0 are needed to compute y2, and y1 cannot be found using 6. Right? So we use the single steps method to find the approximation y1. So the value of y1 must be obtained from another method which you can take single step method. So for example, Euler's method, right? Okay. Now, if you observe, the truncation error is of order h cube here, right? So the global error is going to be of order h square. Now, if you want to have your method to, like, what you're doing, you're computing y2 using this method, but y1 you are going to use some other method to find the approximation, right? So if you want to have the global error as of order h square for this method, you have to compute y1 also using the method which will give you the global error of order h square. Okay, so suppose you use the Euler's explicit method, we know that the global error converges with the order h only, right? So then you cannot expect, because you are spoiling things in the starting itself. So this will spoil things further as well. Okay, so here it's let me write this out as well so that you keep this in mind. So if we can determine y1 with accuracy order h square, then AB method is of AB method has global error of order h square, and that is because the truncation error is of order h cube. Okay, and you can observe one more thing, that this is a two-step method, right? Two-step because you require xk, yk, and xk minus 1, yk minus 1. All right. So this is a two-step method. And the reason is that you require since the values at xk and xk minus 1 are needed in finding value at xk plus 1. So basically you're using two steps, right? So is it okay? Now we have discussed case q equal to 1. Now you can apply the same case when you have any other value of the q. That is, if you have general case for general value of q, what you will do? So you will get the higher order AB methods, but you have to use the higher degree interpolating polynomial, right? So Q is depending. So Q is basically telling that what is the polynomial degree you have to use. So if you have Q greater than 1, that is Q can be 2, 3, whatsoever you want to take it, you can derive the use this idea to derive the method of that order. Okay, so higher order AB methods are obtained by using higher degree interpolating polynomial in the approximation of integrand. So which is the equation where we are using this approximation. So this is equation 3. Okay, 3 and 4. Okay, so for example, if you want to obtain the 3-step methods, so what you have to do, you have to approximate the integral of the gx over this interval by a quadratic polynomial. So you will be approximating it by, let's call it as P2x, where P2x is, so this is a quadratic polynomial. That interpolates gx set. So you're going to require the information at xk, xk minus 1, and xk minus 2. Okay, but for our purpose, q equal to 1 suffice, just to understand that how these methods work. So it suffices to just see the case q equal to 1. All right. Now let's go to the another class of method, which is called Adams Moulton methods, and they are abbreviated as AM methods. Okay, so underlying idea remains the same. That is, we want to find the approximate value of this integral, and we want to use the interpolating polynomial to do that. Right now, only the place where it differs from this Adam-Westford method is the nodes which you are choosing for the interpolation. Right. So here in this method, let's see what are the nodes we are going to choose. So for a given non-negative integer, Q, A methods is use an interpolating polynomial of degree Q on the set of points. So where it differs from the previous method, that here I'm going to include xk plus 1 as well. Okay, so again, you require q plus 1 points, But rather than starting from xk, I'm including xk plus 1 as well. Okay, so we will have xk plus 1, xk up to xk minus q plus 1. So these are q plus 1 points we have it, which will determine the interpolating polynomial of degree q. So we use this interpolating polynomial at these nodes to approximate gx in equation. I think it is 3 or 4. So whichever the equation we have it. So okay, so let me explain this method as well for the case q equals to 1. So q equal to 1, that again we are using the linear interpolating polynomial, but the nodes are going to be xk plus 1 and xk. And let's denote it by p1 again. So let p1x be linear interpolating polynomial which interpolates gx at xk and xk plus 1. Okay, so that is, we have that p1x as, so you can write down its expression. So this is going to be xk plus 1 minus x divided by xk plus 1 minus xk into g evaluated at xk plus x minus xk divided by xk plus 1 minus xk times g evaluated at xk plus 1. Okay, so this distance is again h and this is also h. So I can write this as 1 by h times xk plus 1 minus x times g at xk plus x minus xk times g at xk plus 1. So therefore, the approximation of xk to xk plus 1 gx, the integral of gx over this interval is going to be the integral from xk to xk plus 1 p1x dx. And you can again integrate these terms, okay, and simplify it. So I'm directly writing it. What do we get upon integration? So you're basically having 1 by h times g of xk, integral of xk to xk plus 1, xk plus 1 minus x dx, plus g at xk plus 1, integral xk to xk plus 1, x minus xk dx. And if you simplify this, we will get this as h by 2 g at xk plus 1 plus g at xk. Okay, that is both the factor is going to be h square by 2. So this is also h square by 2 and this is also h square by 2. All right, so this is, see, we have the integral over the interval xk to xk plus 1, and gx is also, we are approximating by the interpolating polynomial with the same nodes xk and xk plus 1, right? So this is simply the trapezoidal rule, right? If you observe. And of the same way, you can find the error as well. And since we have observed that this is a trapezoidal rule, so we already know the error in the trapezoidal rule. So E1G, which is the integral from xk to xk plus 1 gx dx minus integral xk to xk plus 1 p1x dx. So what is the error in the trapezoidal rule? So this is minus h cubed divided by 12. And it will be g prime of the jk. So g is nothing but f, which is y prime. So this is going to be y triple prime at jk. For some jk lying between x and xk plus 1. Okay, so we have the approximation of this integral. Therefore, we can substitute this in the equation number 3. Therefore, from equation 3, we have that y at xk plus 1 this is the y at xk plus the integral of g over the interval xk to xk plus 1, right? So we have already found the value of this. So this is going to be h by 2, keeping in mind that g is denoting f. So this is going to be f at xk plus 1, y at xk plus 1, plus f at xk, y at xk. Okay, and then we have this error term, minus h cubed divided by 12, y triple prime, jk. Is it okay so far? Okay, so we have come to this point. So we can use this to obtain the AM method for this case q equals 1. So thus, we obtain the AM method. So basically, we are just going to chop off this truncation error term. So we'll get this as yk plus 1 as yk plus h by 2 f at xk yk plus f at xk plus 1 yk plus 1. And note that you are not requiring the information like from the previous level. So I could very well have here k greater than equal to 0. Okay. And the truncation error here is this is of order h cube. So therefore, the global error will be all right. And if you observe, this is you want to compute yk plus 1 and you have a yk plus 1 sitting here. And basically for this case, this is nothing but this basically comes down to the same expression what we have for the modified Euler's method. That is implicit Euler method, right? This is the same formula we have got, right? So basically all of these methods, that is the AM methods, they are going to be implicit method because you're requiring that you're using the xk plus 1 as the interpolation nodes, right? So this means that xk plus 1 correspondingly you will have the evaluation of the function at yk plus 1 as well, right? So these methods which you will get using any value of the q, they are all going to be implicit methods. Right. So these methods, if you want to compare these methods with the Adam-Besford method, you will see that, of course, here you might not see a much significant difference. But as you go for the higher order, you will see that the truncation error is much smaller in this case. That is, in case of the AM methods, we have a much smaller truncation error as compared to the Adam-Besford method. Okay. And you can obtain the higher order methods by just using the higher order interpolating polynomial. So the higher order PM methods can be obtained by using higher order interpolating polynomial in the approximation of the integral, which is there in the equation number 3. Okay, so in this case, of course, it boils down that you have got the same method which you have already seen, that is Euler's explicit method. But if you involve, say, one more interpolation notes, that is, if you try to observe that what will happen in the case of the q is equal to 2. So there you will be including xk plus 1, xk, and xk minus 1. Okay, so that formula which you're going to get, that is going to be significantly different from what we have got here. Right, so you will be obtaining a 3-step formula in that case. Okay, so I think like these numerical methods for approximating the solution of the initial value problem, I think this is all I think this is all for approximating the initial value problems. And next, we'll see a method to approximate the boundary value problems. I mean, since we are not having much of the time left, so I think it's better I start it in the next class. So we'll stop here. And I think you all would have received an email that there's a home assignment which is due on Sunday, that is tomorrow, by 10 p.m. Okay, so you all are supposed to submit your solution on Gradescope.
Yes, ma'am.
All right, then if you have any comments or any queries, we can take them now because we have some time left.
Ma'am. Excuse me, ma'am.
Yes.
What benefit we have, extra benefit we have in multi-step method compared to single-step method?
As I said, that see, I mentioned that you have a drawback for the, suppose you want to derive the higher order methods using the RK approach. Okay, so of course, if you just go to the higher order methods, you will see that you need, in terms of the computation, not theoretically, you are not going to see like, you know, how this is going to be benefit, but when you will see the computational costs. Okay, so depending on the expression of the f, if f is having some complex expression, so here these methods, because you're using the information at the previous level as well, right? So there, of course, here you're also using the multiple steps computations for the f, but at the same time you're computing them at the previous steps. So it's like you're just using the information at one previous step, and you're using the information which you have got for the, say, 5 previous steps, right? So you can expect that if you're using more information, you can achieve more accuracy, right? So this is the underlying idea behind this multi-steps method. And for the higher order methods, you will see that if you use these, say, for example, here we have discussed just for q equal to 1. But if you go for the higher values of the q, you are going to use much more information from the previous steps, right? So in that sense, you are going to get better accuracy in this case using the multi-step method. Okay, so if you guys will be interested in this, taking this further, so there's a like, one has to go in much more depth that how the error, like you have to analyze the error, global error. Okay. And you will see numerically also, when you will try to implement these methods, you will observe that, see here, when we are doing the computations by hand, it requires that, okay, if I want to take q is equal to 10, it looks very tedious, right? But if you go to the computer, getting a formula, getting AM method for say q is equal to 1, it's not that difficult because you already have a formula to compute the interpolating polynomial for any value of the q, right? But doing by hand, it looks tedious. So there you will see the real difference if you go to the computer and try to implement these methods. Okay, so it just, you can take it that in these two methods, if you want to compare, of course, the AM method, as I mentioned, that they are going to have a smaller truncation error, right? But if you want to compare it with the single step method, the only advantage you can see here is that here also in the single steps method, you require, when I say single steps, I'm referring to the RK methods because those are the best methods we have there. So you require more functional evaluation, but here also you do the same, but at the same time you basically use the information at the previous levels, so which gives you the better accuracy. Okay.
Okay.
All right. So after just as a plan that since we are left with the maybe 2 weeks of the classes, so we'll just see one method for the finding the approximate solution for the boundary value problem. And then we'll be discussing the numerical methods to to solve basically the system of linear equations. Okay. So I hope you guys are going to like that section because it's, I think, quite going to be quite easy. So yeah. Okay. So if you have any more questions, you can ask now. Otherwise, we'll stop. All right, so I'm ending this meeting here.